Hey everybody. Okay, so this part two of June 2017 Edexcel IGCSE Chemistry Paper 2. This is part 2 of this exam review. I'm doing this for Mita. I know that Mita's been pestering me in order to get this finished, so I'm going to get this done today. I'm just going to... I've forgotten my mouse again, haven't I? Oh, that's frustrating. Have I forgotten my mouse? Very hard. It's useful to have my mouse. Oh no, I've got it. Oh no, the bottom's missing. Missing the bottom panel. There it is. Right. I'm just gonna use the mouse. You see, just it means that what I can do is I can swing the YouTube video over onto my second screen. So it'd be nice to have the paper all done and dusted, and then I'm going to move on to someone else asking me. I've asked video over onto my second screen, and then close it. There we go. Quality of the sound's not brilliant, but I'm using my internal mic. So I'll pop out the chat just because it's the only thing I really need. I'm assuming that Mita will probably turn up. Okay, so I'll share my screen. Let's crack on. Let's just finish off this paper. Won't take very long. 20 minutes, I reckon. Don't need that, because otherwise you're looking at my ceiling. There we go. Okay, so this is where we left off. And so, yeah, this had walked into doing a little bit of organic, which was quite nice. And then it says, so I need to go back to the start of this question really to see what's going on. So they've given us 4 compounds. They've given us ethene. They've given us propene. They've given us an unknown C is a molecular formula, which means it could be but1ene, could be but2ene, could even be 2-methylpropene, could also be that as well. And then, of course, we've also got chloroethane over there. And then it says, explaining which of these are hydrocarbons. Explain which compound has a displayed formula and explain why. So showing all the bonds, that was B. Then we were looking at different methods of making ethanol. So this is methods of making alcohol. Okay, so it then says compound X is an isomer of C. Explain what is meant by the term isomer. Okay, molecules with the same, I'm going to put my little fan on over here just to keep my laptop cool. Molecules with the same molecular formula, but different structural formula. That definition's worth keeping because it comes up a lot at A-level. So yeah, that's isomers. Just to show you what I mean by this, because it's nice to understand this. So C4H8, they've given us in C. Well, in reality, that doesn't really tell us a lot. It tells us the actual number of atoms of each element in the compound, hence the molecular formula, but it doesn't tell us how they're arranged. Yeah, so we could have, this could be but1ene. Yeah, could also be, all the rest, by the way, are H's. All the rest are H's. I could have put the double bond. So they have the same molecular formula, but they have a different structure, different structural formula. Yeah, you could even have this one as well. You could even put the double bond in there and add a branch. When you get to A-level, you'll be looking at how to draw these. There we go. So we can get all of these things from this guy. Same molecular formula, different structural formula. By the way, these aren't actually structural. These are actually displayed, just so you know. These are displayed formulae because I'm showing all the bonds. If you want structural, yeah, you can convert this into CH2, CH, CH2, and then CH3. This guy would be CH3. This would be then CH, CH, and then CH3. This guy would be CH3, which is this guy, onto that carbon, and then you bracket branch. Yeah, CH3, close bracket, that tells me it's a branch, and then CH2. So there, that's actual structural. Students hate structural, they find it really difficult. Okay, so what's happening in this particular, so this is a hydration, because we are adding water. I like it. You could also say that you could also call it an addition reaction. That's interesting. They're calling it a hydration. 2 correct answers, and that's why. RTFQ, tick the boxes that show the 2 correct answers. Dehydration is the removal of water, so you'd have H2O spat out there for dehydration. And oxidation, usually a GCSE will contain oxygen going in. Yeah, but not always, just to bear that in mind. And a reduction usually has oxygen being removed from somebody. So in this case, hydration and addition. Right, compound D, chloroethene, can be used to manufacture PVC. State the full name of PVC. Polyvinyl, I know it's weird, vinyl chloride. Now, there's actually another name for this as well, which is polychloroethene as well. It'll be interesting to see the mark scheme, polychloroethene. Now, I'm assuming they're going to allow both. This one here is the old name. This is an old name, vinyl, meaning ethene. And whereas the other one, this one here is modern. This is up to date. I'm assuming they'll allow both. Be interesting to see the mark scheme on that one. Write an equation containing displayed formulas represent the reaction that occurs in the manufacturing of PVC. Right. So whenever you're drawing polymers, the first thing that's got to go in is you've got to go in your monomer. Yeah. So a monomer is a single unit, doesn't have to actually be containing a double bond if you're making a polyester, but this is a polyalkene, so we need to add in chloroethene, which is this guy. Now, you could have put, just to let you know, you could have put the chlorine on any one of the carbons. It really wouldn't matter if you wanted to put it there or you wanted to put it there. You can put it wherever you like. It doesn't matter in this particular example. I'll put it there since I've removed it. Right, now what we're going to do is we're going to put n number of these in. Now, n means many. So that's now going to join together. The double bond breaks. The double bond breaks in the middle, and these long bonds extend outwards. So what's happening is this bond here is flipping open, is breaking open to allow it to make 2 new bonds. The other people are still attached. They don't change. Yeah? And then what you then do is put in a bracket followed by the letter N. So there's my monomer going to my polymer. Definition of a polymer, by the way, a giant molecule made of many repeating smaller units, which were monomers. Notice the were there, by the way, that's kind of important. A giant molecule made of repeating units, which were monomers. They'd all join together. They often ask, it'd be interesting to see whether or not this comes up. It often, okay, it hasn't there. They've deleted that question. It just means when they build papers, they had extras. So common questions that often come up. So number 1 is, what is a monomer? 1 mark. Monomer, question mark. What is a polymer? Question mark. And also describe polymerization. Polymerization. So this is the process of making a polymer. So a monomer is a single, I'll do it in red, a single unit that can be used, that is used to make a polymer. Now, the thing is, if they put this in a context, which every now and again they do, if they said describe an alkene monomer, then you'd actually have to say, a single unit that is used to make a polymer which contains a double bond. Now, this doesn't always apply because if you're making a polyester, they don't have a carbon-carbon double bond. So this is a much better definition there, really. Well, in the next couple of papers, I'm sure one will come up and we'll see that. So the definition of a polymer, a giant molecule made from many repeating units, brackets, monomers. There we go. By the way, it's nice to also get you to realize that the monomer, of course, has a low boiling point. This has a low BPT because it's a small molecule. It's simple covalent. There are weak intermolecular forces between the molecules. These are very weak. There are very few. little energy to break. And I'm running Susan Boyle there, if anyone doesn't know. That's Susan. I'm just running my process for doing boiling point. Yeah, Susan Boyle sings Nellie the Elephant. So the structure is simple covalent. The monomers are simple covalent structures. The bonds are the weak intermolecular forces between the molecules. You've got to say that word, between. Yeah, between molecules. Yeah, so simple covalent, weak intermolecular forces. Strength of these forces, very weak. WIMPs are very strong. You can't write WIMP in your exam, by the way. You have to translate that into weak intermolecular forces, but it's easier to remember WIMP. WIMPs are very weak. There are the number of them. There are very few of these bonds. There are very few of these forces, these bonds. Energy very low to break. Not much energy needed. Energy to break low. Yeah, I'm just running it. And then, of course, we then form a polymer, which then has a much higher boiling point. So this now has a high boiling point. They're usually solids at room temperature. Most plastics are. In fact, all plastics are. And the reason why is because it becomes a giant covalent structure. And therefore, we're going to have, we do have covalent bonds within the chains, and then weak intermolecular forces between the chains, but they're massive. So the weak intermolecular forces are stronger than they were in these ones. And you've got to break the, so it's, yeah, so stronger weak intermolecular forces. Just to explain what's going on there in a diagram. So here's the ethene monomer. Here's an ethene molecule. Yeah, and I call it a monomer there because it's specifically in a polymer setting. So if I have multiple ones of these, yeah, these are my WIMPs, and they're very weak. Yeah, WIMPs, weak intermolecular forces. Now, just to let you know that WIMPs are special because they actually grow with size. So the bigger the molecule, the stronger the WIMP. You'd never say strong WIMPs because they're not. So if that's a monomer, well, a polymer is going to be thousands of those joined together. And I mean like thousands, hundreds of thousands, maybe even millions. Yet the molecules become these. You know, they're massive, repeating units of the same thing over and over again. They're massive structures. So the WIMPs between them are now stronger. So the boiling point increases. Look how many more there are. You know, you just say that the WIMPs are stronger. Yeah. So this is now polyethene. Polyethene. So the key thing here is bigger molecules have stronger weak intermolecular forces, so higher boiling point. Describe polymerization. So the double bond, bullet point number 1, the double bond, I'm just going to put DB, the double bond in the monomer, I'm just going to show you this then, ethene. I'm just going to draw it out. I like to see pictures, you see. The double bond, I do everything in pictures in reality, and then I turn the pictures in my head into words. The double bond in monomers break open. Break open. So it now becomes this. Yeah. Those now join together. Breaks open. Join together to form one giant chain, one giant molecule. So the double bond vanishes. So it's just nice to, so that's it, that's all you need to realize. The double bond breaks open and they join together to form one giant molecule. That can actually be 3 marks in an exam. Can. The double bond in the monomer breaks open and they join together to form a giant molecule. So it can actually be 4. You wouldn't usually, these two are usually tied together. You can't just say the double bond breaks open, you have to say the word monomer to get the mark. That's the stupid thing, isn't it? Anyway, it's nice to talk about polymers a bit. Okay, on to enthalpy change. So straight away, by the way, I know that this is external calorimetry because the methanol is burning, we're heating up water, we're collecting the heat. So question number one. There are several reasons why the increase in temperature is less than expected. One reason is the incomplete combustion to form only carbon monoxide and water. Write an equation for this incomplete reaction. So they've they've noticed they've not actually given us the formula. Oh, they did. Oh, GCSE. So they've given us the formula of methanol. This is a structural, by the way. I'm going to add in oxygen because we know, because it's a combustion. All combustions add in O2. Yeah, and we're going to form, and it tells us what to make: carbon monoxide and water, CO and H2O. Now we're going to balance it. Don't forget to balance. 1 carbon, 4 hydrogens, 3 oxygens. Oh, 3 oxygens balances. Nice, done. Next, state another reason why the increase in temperature is less than expected. So the number one reason why this experiment is garbage is heat loss to the surroundings. Yeah, this is garbage. Yeah, it's just going to escape. Some of it will go in. Yeah, but most of it's going to be heat loss. So that's the top answer. There are an awful lot of these, though. So just to point out the others that we tend to get. Number 1, incomplete combustion. Always a good one. By the way, that's only if you're burning incomplete combustion. If it was a reaction between like a metal and an acid, you could say an incomplete reaction. That's another one. Incomplete reaction for something non-combustion-y. The other one, of course, is heat loss to the environment. They tend to remove this one, heat loss to environment, because it's a little bit vague, really. Can I just point it's not really that vague. It tells you exactly what's going on. It's escaping to the environment. So heat loss to the environment is number 2. Number 3 is evaporation of water. So evaporation, evap of water, because that's going to cool it. You know that, you guys all know that when you put water on your hands feel cold. That's because the water is evaporating, and the energy in your hands is going in to break the weak intermolecular forces between the water molecules, which means you're absorbing your heat, and then the molecules are escaping with your energy. So evaporation of the water, that's why an improvement of this would be put a lid on it. That would make things immediately better. The other one is evaporation of the fuel, which is far less likely, since there's a lid on the fuel, but they do like that one at Excel. I don't really like it. They're saying that you could get evaporation off the string, that you've got evaporation going on down here, because the wick is going to wick up the fuel, and then some of it's going to evaporate that way. So evap of fuel as well. So it's just nice to mention these. Incomplete reaction as well is a separate one, because it's a different reaction. Incomplete reaction. Yeah, always nice. Incomplete reaction. Other ones include impurities. Impurities. Now, you can't use this one for the fuel, impurities. You can't use this one here. The reason why is because if the fuel was impure, then it wouldn't burn in the first place. So that's one you can't use for this particular example. Sorry about that, but it's a good one to know. It's in your repertoire. So in this case, I'm going to put heat loss. Top answer. I'm going to put heat loss to environment. They'll all be there. Heat loss to environment. It'll be interesting to see if this is not ranked number 1 by Edexcel on their mark scheme. It'll be interesting to see. Next, right, Q equals MC delta T. What is the mass of water in grams? And delta T. So just a 2-mark question, nice and easy. So we're just going to find out what M is, the mass of water. It's up there in the data. M is the mass of water, grams. So we're going to input the data, M there, 4.2, and then the temperature change, right? That's the first bit of maths we've got to do. Remember, don't do this in your head. Please do it on your calculator. You will make a mistake. It's just not worth it. It's more reliable to use your calculator. 36 degrees, 1 mark. Input it into here to work out Q. So I now have 125 multiplied by 4.2 multiplied by 36. And I'm going to get an answer in joules, remember. This equation spits out in joules. Times 4.2 times 125 equals, I get 18900. Next, I like it. The relative, so this next one is the fact that whenever we have calorimetry, calorimetry is whenever you're trying to collect heat in water. There are actually 2 equations. I'm going to show you both the equations over here. So it's actually a 3-step process. This is calorimetry. Calorimetry. So we have Q equals MC delta T. This is all about the water. This is catching the heat in the water. Step number 2, divide by 1,000. People often ask me why. The reason being is this equation spits out the energy, Q, in joules. It's raw energy. Yeah, raw energy. Whereas what we're trying to get to in the third equation, delta H equals Q over N, the enthalpy is in kilojoules per mole. So we need to remember to convert this to kilojoules, hence the divide by 1,000 step. And then you just divide it by the moles. By the way, teachers often don't teach this equation. They often don't bother. And the reason why they don't bother is because the equation is in the units. So we know that this little slash here means per. Well, in reality, like, it doesn't. It means divided by. Yeah, this equation, which we write down like that, what would be a better way to write this down is kilojoules over moles. It is the equation. Which is always nice. Once you start realizing that, the units become super handy in being able to do calculations in chemistry, because often you forget the equation, and then the question will tell you the units, and then it tells you the equation. That's amazing. Wish I'd been told that when I was studying. It would have been really handy. I didn't get told that when I was studying. So now that we've got our number of 18900, what we now need is the moles. And we know that there are 3 equations for moles. Number of moles is grams over rams. Can I just please ask, I keep seeing my year 11s make a really silly thing where they don't bother with the N. They just write down this. Please don't do that. Please include the N. It is important. Moles is C times V over 1,000. That's concentration times by volume over 1,000. And then, of course, number of moles is V over 24. If we're in liters, this is for gases. There's another version of this, of course, which is very common, which is V over 24,000. And that's because we're now in centimeters cubed of gas. So just bear that in mind. So in this case, which one have I been given? I've been given its MR. There's the molecular mass, relative molecular mass. I've been given its RMM. Right, and we were told how many grams we burnt. So step number 1 is we need to work out how much fuel we actually burnt. So 84.7 minus 83.2 equals, calculator, 84.7 minus 83.2, checking my numbers again, and that's going to give me S to D. I am burning 1.5 grams, mark number 1. Right, next, now that I've got the grams, I can work out the moles. Number of moles is grams over rams, and I'm working this out for methanol. So the number of moles is 1.5 over the relative molecular mass of methanol, which is 32. They've given it to me. That's rather nicer than why, thank you. 1.5 divided by 32. That's going to give me 0.0469 rounded. Keep the number on your calculator. Moles, Christmas moles. So there's moles of methanol. It's just about moles of methanol. It's just nice for us to do that. It's good chemistry. It helps remind us. Right, now that we've got that, now all we do is take the number we had before, 18,900, divided by 1,000 to get 18.9 kilojoules. So I'm doing, by the way, just to explain what I'm doing here, I'm doing delta H equals Q over N. So my Q is going to be 18.9 because it must go in kilojoules, divided by my moles of 0.0469. I've got that number on my calculator, which is actually 0.046875. And now I'm going to do 18.9 divided by answer equals S to D. And I get an output of 403. We're about to make a mistake. 403 kilojoules per mole. But I've now made a mistake because this was a combustion. This is exothermic. And what we must remember, so the easiest mark to lose on the paper, you've got to remember to add in your minus sign, because that minus tells us is exothermic. So the final answer on the line is minus 403.2. I would actually leave that one as positive and then add in the minus sign on the answer, but in reality, they don't care. Yeah. Cool, because you can't, yeah, that's actually, I can put it there as well. Cool. Next. Right, what's wrong with the diagram? Okay, so these are heat energy profiles. So the first thing to realize is, just to mention these two graphs, exo minus delta H and endo, positive delta H. Can I just say, mathematicians in the room, please, 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 please don't forget to include that plus. I know that your mathematicians teach you, your maths teachers teach you, well, you don't have to show the plus, because if you've got 50, that's the same. That is the same as 50 plus, because the invisible sign means it's just a plus. That's not the same here, folks. The reason being is this symbol actually means something. It means endothermic. So do watch out for that. Lots of students see the fact that their calculator doesn't have a plus and then they forget it. Right, so two graphs. The exothermic graph drops. That's exo. So we're going to have the reactants on here and the products on here. An endo graph goes up. Just to explain to you what's going on in this. So this arrow here, we're going to take the reactants. So let's go super simple. Let's go hydrogen and oxygen. Hydrogen and oxygen. And what we do is, the first thing we've got to do is we've got to heat this up. We're actually having to increase the temperature. The reason being is we need to break the original bonds. So this arrow here is called the activation energy. This is EA, activation energy. But in terms of bonds, you could also see that this is the energy to break original bonds. Energy to break ORI bonds. Yeah, this is the original bonds. Now, once those bonds are broken, the atoms are then going to recombine. They're going to find new bonds. And when they find new bonds, they're going to turn into the products. So in this case, it's going to form water. I probably ought to balance the equation, really. There we go. Something to it. There you go. I can balance it and add another hydrogen up here. There we go. That now all adds up. There we go. So we're going to make the new bonds. This arrow here represents the energy released when the new bonds are made. Energy released. Energy released when new bonds are made. When new bonds are made. So just to tell you, by the way, one of the most amazing things I've ever picked up in my teaching is mexobendo. I didn't invent this, by the way. This actually came from one of my year 12 students, mexobendo. Her name was Kate. Such a lovely student. And she came up with this little rhyme that I didn't invent, but I absolutely adore. And what this says is mexobendo, making bonds. This is super handy. It's one of the most important things in chemistry. Making bonds is exothermic. And breaking bonds is endo. It's super handy. I cannot tell you how useful this is. And I didn't invent it. Bonkers. But it's so good. It's absolutely unbelievable. Making bonds is exothermic. Breaking bonds is making is exo. Breaking is endo. It's really, really handy. And this just reminds us of what's going on here. So to break the new ones, I should have color coded this. To break the originals is endo. That there is add heat. And then the making is exo, minus heat. So there's more energy being released in the new bonds than it took to break the originals. This means that the bonds in the new compound are stronger. These bonds here, so amazing to understand this. These bonds here are stronger than the original bonds. They're stronger. It looks like they've gone down, but they haven't. They're actually stronger because they're releasing way more energy when they're being made than it took to break the other ones. So the overall heat change, by the way, this is the enthalpy change, the difference between the two shelves. This is delta H. And in this case, it's exo because it's going down. I'll get rid of that. There you go. So this one is endo. So this one is to break the original bonds. Let's just do this as X bonded to X and Y bonded to Y. So to break those bonds cost me a huge amount of energy. I mean, like mammoth. It's huge. Look at it. Very endothermic. Massively. Bendo. Breaking bonds. Then the new bonds are going to come. I'm going to make then the bonds to X, XY, and XY. And you can see the pathetic amount of energy released by this new bond. These bonds here are much weaker than these bonds here. So it's an endothermic process. The overall heat change is here. This is the enthalpy change. This is delta H. And it's positive because it's going up. I shouldn't use the arrow at the bottom, should I? There you go, because the arrow's going up. So endo and exo graphs, really nice to understand what's going on there. A very common question is to do with the bonds, and everyone gets it reversed because of the picture. So straight away, we realize that we've just calculated this to be exothermic. It's combustion. So they've drawn us an endo. No, this is not an endo. That should have been down there. So the first mistake is that the products should be lower than the reactants. Products should be lower in energy than reactants. The next thing, one of the reactants is missing. Yeah, because we've got carbon dioxide and water on our product shelf, which is perfect. We've got methanol over here, but where's the oxygen? We're missing the oxygen. So oxygen missing from reactant shelf. from reactant shelf. Shelf. By the way, lots of students go, there's no line between the two. You're right, but they don't actually need to show that line all the time. It's actually really annoying because it is missing, and Edexcel don't accept it as an answer, which really frustrates me, because if they're going to do it, they ought to link them together. But there were bigger, more pressing concerns here. Yeah, the line between them is just to show you what's happening in terms of bonds making and bonds breaking. This is showing us that it's exothermic, and the missing oxygen is really important. So there are more pressing matters at hand. If they ever ask you to do this, and this is quite common, please just don't write down. They haven't drawn a line between them. Don't do it. Right, continuing with energetics, they've given us bond enthalpies. How lovely. Now what we're going to do is we're going to run burp. Reactants minus products. So this here is all about the data. I've been given bond data. So my B stands for bond data. So all I've got to do now is split my equation in half. Right, smash all the reactants first. Right, so over here, I am going to smash 3 carbon-hydrogen bonds. So in my exam, here's how I do this. This is 4 marks, guys. This should take 4 minutes. I'm actually going to put burp over here. I like burp being matched. It helps me out. So I've got to do CH bonds. I've got to smash 3 of them. And the strength of those is 4, 1, 2. Right. I've then got to smash a CO bond. So 1 CO bond at 360. Then I've got to smash 1 OH bond. 60. 1 OH bond at 460. So 1 OH bond times 1 at 463. Right, now I've got to break the oxygen bonds, and there's 1.5 of them. It's a trap. Yeah, so I've now got O double bond O times 1.5. Because I've got a number on the outside, that's 496. Right, total it all up, folks. Here's my reactants. Right, 412 times 3 plus 360 plus 463 plus brackets 496 times 1.5 brackets go. Total 283. Right, first I've gained my first mark. Next thing, smash all the products. Right, CO bonds. So I've got C double bond O, and I have 2 of them in the picture. There's no big number. That's useful, so I don't need to worry about it. So this is just times by 2, and that's over here at 743. Strong bond, that very strong. And then the water bonds. I've got 2 OH bonds in the waters, in each water molecule, but I've got 2, so times 4. There's the trap. There's the trick, guys. Everyone's going to miss that. Be careful. Don't be that guy. Yeah, 743, or that girl, times by 2 equals plus brackets 463 times 4, close brackets. Total number 3338. So it's nice to show, number 1, that this process over here was endo. Break the original bonds. Yeah, we can turn this into a graph if you like. Yeah, here's my reactants. Yeah, in this case it was methanol and oxygen. Yeah, I'm going to put M and O2. Can't just methanol and oxygen. I'm going to smash that and erase that. Woo! Raise that right up to here. And that arrow there is plus 2803. I've now smashed everything into atoms. Carbon, hydrogens, I've got a couple of oxygens lying around over here. I've smashed it into atoms. And then what happens, this is the endothermic process. Yeah, and then what's going to happen is they're going to reform. This is the exo process. And we've just worked out that that's going to release minus 3,338. That's massively exothermic. So, by the way, I'm just showing you that they're endo and exo processes. Well, in reality, all you now do is take these 2 numbers, don't add any signs, and just minus reactants. The bond data is reactants minus products. Just use these numbers straight out your calculator. So 2803 minus 3338, go. Gives me minus 535, and I'm done an exothermic process. Whoop, whoop. Winner. Cool. And I believe that brings us to the end of the paper. Now, I'm just going to really, really fast have a look. I wonder if I've got the mark scheme there. I didn't include the mark scheme. These are all the correct answers. You're more than welcome to have a look at the answers. I should really mark it at this point. I probably can. I probably have the paper line around somewhere. Mark scheme tune, there you go. So I can split my screen now so you can see the two. So if I split my screen up, oh, didn't want to do that. If I split my, I've got messages all over the place. So, okay, yeah, split my screen, sorry. Right, hang on. Get in there. Just gonna move that over to here. Perfect, there we go. And then I can zoom in a bit just to make it fit the page. Let's go all the way through the paper because I believe I didn't mark this last time. I believe might have, but anyway, it's always nice to go through these things. So, question number 1, way up here. Okay, so let's run through the answers. Let's just check this mark in green, I guess. So C, I like it. 2 on 1, don't need the 2s, that's good. I like it. Next, top and bottom, tick, tick. Thank you very much. I know that this is not going to make an awful lot of sense. Next one, D, thank you very much. B, thank you very much. C, thank you very much. 28.1, thank you very much. Plus method. Yeah. Next, dot and cross diagrams. Please do so show the circles. I know that if overlapping circles stroke touching, use both electrons must be within the overlapping touching area. Yeah, just to say, I don't like the fact that Edexcel are like the only exam board who don't really like these circles, which is really weird because the circles are really, really important. It actually makes it so much easier to know, to be able to like piece things together. And what they're saying here, this little bit here is important, isn't it? And what they're saying is if you're doing an overlap, yeah, you're doing circle over, the electrons need to be in the gap. Yeah, just letting you know. Yeah, they don't like little stupid things, you know, they don't like people doing stuff like this or this, you know, don't do that. Just put them in the middle. Yeah, anyway, fine. So if you don't like doing the circles, don't do the circles. I'm totally fine with that. 2 marks. The fluorine, of course, is the one that everyone forgets to add up to 8. Right, now we're going into a bit of bonding, which is nice. I run Susan Boyle on this. So intermolecular forces between molecules, I like it. Simple covalent, yeah, simple covalent is a larger molecule, stronger in this, stronger weak intermolecular forces, there you go, yeah. So we get both marks there. So what we're saying is that they're both simple covalent. This is larger, yeah. So it's larger, so we have bigger MR. So the stronger weak intermolecular forces, yeah, we're done. Yeah, that's fine. Tick, tick. Weak intermolecular forces, stronger in CiCl2. Next one, you've got to run Susan Boyle again because it's giant covalent. This is silicon dioxide. It has strong covalent bonds, whereas, oh, it's a comparison. Oh, yeah, okay. Yeah, so we say this one is strong, is giant covalent, unlike this one, which is simple. This one contains only covalent bonds. Yeah, must be broken. This one contains weak intermolecular forces. These are stronger. We're good. We know this is okay. Next one, the electrons from the wires, unreactive, not reactive, allow unreactive, does not react, not chemically reactive. Oh, good grief. Is there anything it doesn't allow? Next, needs to be heated strongly so it melted, so the ions become free to move. Whoop, whoop, winner, take it. Next, chlorine and oxygen. This is a horrible equation, hardest question on the paper. Yeah, and all the half equations that go with it. It's disgusting. Ugh, horrible. Yeah, all kinds of funky stuff going on there. Right. So I was then running, there you go, 1 point, that's interesting, except 1.27. That's weird. Why would they want anything else? Anyway, this was the electrolysis calculus. These are dead now, guys. You do not need to do this. I've got the right answer, 1.27, 1.3 grams. But you do not need this anymore at GCSE. It's gone. It's been removed. It's nice. A, B, and C are hydrocarbons only. Only, there you go. Only over there. Only. B, because it shows all the bonds, shows all bonds in the molecule. Yeah. Pros, cons, it's fast, it's continuous. Is they got continuous there? Oh. Do not need further processing. That's weird. Well, they've got that wrong for a start. Mine is correct. I know mine's correct. Stupid. They've given a greater atom economy and then not done continuous and this. Stupid. Edexcel. That is correct, by the way. They can stuff off. M5 renewable. I like it. Low energy needs. Yeah, it works at low heat. I like it. Uses and does not work at. I put carbon neutral. Sustain climate. Ignore reference to batch or continuous. Whatever. What? All right, I'll take it off. Mental note. They don't like continuous. What? That's the most ridiculous thing ever. I won't get lost in this. Yeah, I won't. It's fine. Next. Butene. Oh, they wanted the 2. Except butene. There you go. So they accepted without the 2. Colorless. I like it. Isomers. Molecules with the same molecular formula and the different structural formula. Boom, boom. Thank you very much. There you go. 2 of those. There you go. Nice. 1, 2, 3. Winner. 1, 2, 3. I'll have those. Thank you very much. Balanced equation for incomplete combustion. Like it. Heat loss to the environment. Thermal loss to the surroundings. Yay. There you go. Top answer. Our survey said. Winner. The other one. There you go. Evaporation of water or methanol. Isn't that lovely? Lol. Love it. But it was our survey said top answer. 18,900. Thank you. I'll take it. And then minus 403. Thank you very much. Give me the proper number, please. Thank you. Tick, 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 tick. All of it. All of the above. Right. Mass. Yada, 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 yada. Weird. Is that B again? Oh, we're going 2 minutes. That's weird. Well done there. Anyway. Oxygen reactant is missing. Level lower. Except probably should be below reactants. Ignore reference to activation energy. Reference to missing. Ignore reference to axis X. Here, axis X is weird. Because that technically is like time. It's not even time. It's position and reaction, start and end. Weird. Really weird. So you ignore that one. 2 answers, by the way, are correct. Just no, it's our survey said this is like a family fortune. There we go. 203, tick for 1 mark there. 203. Next one, 3338, tick there. Calculate the difference in the 2. Oh, that's not weird. Where's the final answer? And then it just says that negatives, ignore negative sign, reference, expected final value is, yeah, minus 535. I like it. Difference between the 2. They're saying error carried forward. That's what they're doing. And then give the negative sign. So we're good. Oh, well, I definitely lost one. I will take it on the chin. Guys, Edexcel don't like continuous. And that is a complete load of garbage. That's not okay. So what they want in this one is the reason why. Okay, what they're saying is that there are more important things. I get it. Fine. This one here, direct hydration, super fast. Heck yes. And the product is pure. Yeah, pure product. Definitely. I'm happy to take it on the chin and make that adaptation myself. They want you to say pure product. Yeah. The next one, though, again, renewable, yes, and then high labor. I mean, what do they want? I need to know this. I need to fix this because you know I've got all these answers in my head and they're not giving them to me. So let's find it. And this is something I need to make an adaptation for. Happy to do it. It's further up, was it? There, right. So it is not renewable. So I definitely got them. This one is renewable. Yes. The low energy does not need much energy. Yeah. Okay. I get that one as well. So top answers. Yeah. Why aren't they accepting carbon neutral? They're saying that it probably isn't okay. In reality, it probably isn't okay. So scrap carbon neutral. Yeah. Low pressure. They're saying that you say that the other reason is because it's done at low pressure. It's weird because it comes under the energy concept. I don't really like that, to be fair. Yeah, renewable. Okay, fine. Fine. So I'll stick with those. That's worthwhile knowing because this comes up a lot. I'm going to end my webinar there today, guys. A nice, easy end of paper 2. Meter, I hope you find it useful. Let me know what paper you want me to do next. I think I've been asked to do 2016. So I'll have a look at the 2016 C1 and C2. Guys, have a good rest of your day, and I'll see you soon.